A fox finds an opossum. The opossum has no claws worth mentioning, no venom, no speed. Its entire defensive strategy, refined over 70 million years of evolution, is toe fall over, just completely collapse. Eyes open, tongue out, a smell that cannonly be described as aggressively deceased. And the fox, an animal with functional teeth and a working nose, looks at this performance. Decides it's not interested in a dead opossum and walks away. The opossum waits, gets up, goes about its evening. This worked. This has always worked. And the most unsettling part is that the opossum didn't choose to do any of it. Its brain made that decision without asking. Today, we're talking about tonic immobility, the scientific name for playing dead. It happens in opossums, beetles, sharks, ducks, rabbits, and in a very specific and deeply uncomfortable way. In humans too. And once you understand how it actually works, you will never call it playing dead again. Let's start with the opossum, because the opossum deserves a moment of genuine respect. The Virginia opossum is North America's only marsupial. It has been around, largely unchanged since the time of the dinosaurs, 70 million years of survival. And its primary defensive innovation is collapsing dramatically in front of predators and emitting the smell of a small biological disaster. Here is what actually happens during tonic immobility in an opossum. The animal does not decide to play dead. The nervous system makes that call automatically when the threat level crosses a certain threshold. Heart rate drops, body temperature drops slightly, muscles go limp, the animal falls over, sometimes mid-step, and stays there. The eyes stay open, which is unsettling, the mouth falls open, the tongue lolls out, and then the really committed part, glands near the tail, release a secretion that smells genuinely, chemically identical to the compounds produced by a decomposing body. The opossum is not pretending to be dead. The opossum's body is putting on the most convincing possible biochemical performance of death that evolution could design. And it works because most predators have a strong instinct against eating anything that is already dead and already smelling like it has been dead for a while. Scavengers aside, a fox or a coyote that eats a random dead thing it found is a fox or coyote with a high risk of food poisoning. The opossum exploits that instinct with remarkable precision. The performance can last anywhere from a few minutes to 4 hours. The animal has no control over when it ends. The nervous system decides when the threat has passed and essentially reboots the body. The opossum gets up, shakes itself off, and continues with its evening as if nothing happened. Because from its perspective, nothing did. The opossum gets all the credit for this behavior, but there is an animal that has taken tonic immobility to a level of engineering that is genuinely impressive. The death-feigning beetle, and yes, that is its actual common name, someone decided to just call it exactly what it does, can enter a state of complete immobility within milliseconds of being touched. It drops. Legs in the air. Antennae flat. Completely still. And here is where it gets interesting. Researchers studying these beetles discovered that the beetles which stayed still longer survived at significantly higher rates than the ones that got up quickly. So evolution ran a very long experiment that essentially asked, how long can you stay convincingly dead? And the answer it arrived at was longer than you think is necessary. Studies found that beetles with higher stress hormone levels at the moment of threat stayed immobile for longer periods. The stress response that usually prepares an animal to fight or flee was being redirected into staying absolutely, perfectly still. The same chemicals that make your heart race and your muscles ready to move were being used by the beetle to do the opposite. It converted panic into stillness, which is either a remarkable evolutionary trick or the most relatable thing an insect has ever done. Now here is where tonic immobility stops being cute and starts being genuinely strange. Sharks do this too. If you flip a shark upside down and hold it still, within about 15 seconds it enters a state of tonic immobility. Eyes roll back, muscle contractions stop. The animal becomes completely passive and stays that way for up to 15 minutes. Marine biologists use this technique to temporarily immobilize sharks for tagging and examination without anesthesia, which means there are scientists whose job includes flipping large sharks upside down by hand and waiting for them to calm down. And it works. Every time. The shark does not choose this. The inversion triggers an automatic neurological response that the shark has no control over. Orca whales figured this out independently. There are documented cases of orcas holding sharks upside down to immobilize them before eating them, using the shark's own nervous system against it as a hunting strategy. A predator weaponizing another predator's involuntary shutdown response, which is, by any measure, a deeply sophisticated thing to figure out. And it raises an obvious question. If this response can be triggered from the outside, by inverting the animal, by a specific physical stimulus, what exactly is the nervous system responding to? And why does something this fundamental exist in animals as different as a marsupial, a beetle, and a shark? Here is the part that connects everything. Tonic immobility is not a behavior in the way that running or hiding is a behavior. It is a neurological state, a mode. Something the nervous system switches into when it has calculated that all other options have failed or are unavailable. Fight is not possible. Flight is not possible. The predator is too close, too fast, too certain. And at that point, something very old in the brain takes over and does something that seems completely counterintuitive. It shuts the body down. The theory is that this response evolved as a last resort because it works in several ways simultaneously. First, many predators lose interest in prey that has stopped moving. The movement is often what triggers and sustains the attack response. Stop the movement and the predator's interest can drop significantly. Second, the biochemical signals of apparent death, the smell, the limpness, the open eyes, actively repel predators that avoid carrion. Third, stillness eliminates the sound and movement cues that other predators in the area might use to locate the animal. It's not just about the immediate predator. It's about not attracting additional threats. The system is ancient. It shows up in species that diverged hundreds of millions of years ago, which means it evolved very early and was kept because it kept working. Your nervous system has a version of this. When humans experience extreme threat, assault, accidents, situations where neither fighting nor running is possible, the same system activates. Heart rate can paradoxically drop. Muscles go limp. The person becomes passive and may feel detached from what is happening. Trauma researchers now understand this as the same fundamental neurological response, not weakness, not a choice. The oldest survival program in the vertebrate nervous system doing exactly what it was designed to do. Two more examples because the range of this behavior is genuinely surprising. Ducks. When a duck is grabbed by a predator or by a researcher, which from the duck's perspective is probably indistinguishable, it will frequently enter tonic immobility within seconds. Wings flat, neck limp, eyes partially closed. Farmers have known about this for centuries. The old term for it is duck hypnosis, and it can be induced simply by holding the duck firmly and tilting it onto its back. The duck is not hypnotized. The duck's nervous system has decided that the situation is unwinnable and switched to shutdown mode. Rabbits do the same thing. A rabbit caught by a predator will sometimes go completely limp, and this is not always fatal. There are documented cases of predators carrying limp rabbits back toward their den only for the rabbit to suddenly come back to life and flee when the predator loosens its grip. The tonic immobility created an opportunity that running could not. The predator relaxed, the grip loosened, the exit appeared, and the rabbit, whose nervous system had been waiting for exactly that signal, was running before the predator understood what had happened, which is honestly a more sophisticated escape strategy than most animals have access to.